In calculus, Taylor's theorem gives an approximation of a k times differentiable function around a given point by a kth-order Taylor polynomial. For analytic functions, the Taylor polynomials at a given point are finite-order truncations of its Taylor series, which completely determines the function in some neighborhood of the point. The exact content of Taylor's theorem is not universally agreed upon. Indeed, there are several versions of it applicable in different situations, and some of them contain explicit estimates on the approximation error of the function by its Taylor polynomial. Taylor's theorem is named after the mathematician Brooke Taylor, who stated a version of it in 1712, yet an explicit expression of the error was not provided until much later on by Joseph Louis Lagrange. An earlier version of the result was already mentioned in 1671 by James Gregory. Taylor's theorem is taught in introductory level calculus courses, and it is one of the central elementary tools in mathematical analysis. Within pure mathematics, it is the starting point of more advanced asymptotic analysis, and it is commonly used in more applied fields of numerics as well as in mathematical physics. Taylor's theorem also generalizes to multivariate and vector-valued functions f, R n room on any dimensions n and m. This generalization of Taylor's theorem is the basis for the definition of so-called jets which appear in differential geometry and partial differential equations. Motivation. If a real-valued function f is differentiable at the point A, then it has a linear approximation at the point A. This means that there exists a function h1 such that here is the linear approximation of f at the point A. The graph of y equals p1 is the tangent line to the graph of f at x equals a. The error in the approximation is, note that this goes to 0 a little bit faster than x minus or as x tends to a, given the limiting behavior of h1. If we wanted a better approximation to f, we might instead try a quadratic polynomial instead of a linear function. Instead of just matching one derivative of f at a, we can match two derivatives, thus producing a polynomial that has the same slope and concavity as f at a. The quadratic polynomial in question is Taylor's theorem and shows that the quadratic approximation is, in a sufficiently small neighborhood of the point a better approximation than the linear approximation. Specifically, here the error in the approximation is which, given the limiting behavior of h2, goes to 0 faster than 2 as x tends to a. Similarly, we get still better approximations to f if we use polynomials of higher degree, since then we can match even more derivatives with f at the selected base point. In general, the error in approximating a function by a polynomial of degree k will go to 0 a little bit faster than k as x tends to a. This result is of asymptotic nature. It only tells us that the error rk in an approximation by a kth-order Taylor polynomial pk tends to 0 faster than any non-zero kth degree polynomial as xa. It does not tell us how large the error is in any concrete neighborhood of the center of expansion. But for this purpose there are explicit formulae for the remainder term which are valid under some additional regularity assumptions on f. These enhanced versions of Taylor's theorem typically lead to uniform estimates for the approximation error in a small neighborhood of the center of expansion. But the estimates do not necessarily hold for neighborhoods which are too large, even if the function f is analytic. In that situation, one may have to select several Taylor polynomials with different centers of expansion to have reliable Taylor approximations of the original function. There are several things we might do with the remainder term. Estimate the error in using a polynomial pk of degree k to estimate f on a given interval. Find the smallest degree k for which the polynomial pk approximates f to within a given error on a given interval. Find the largest interval on which pk approximates f to within a given error. It is also possible that increasing the degree of the approximating polynomial does not increase the quality of approximation at all, even if the function f to be approximated is infinitely many times differentiable. An example of this behavior is given below, and it is related to the fact that unlike analytic functions, more general functions are not determined by the values of their derivatives at a single point. Taylor's theorem in one real variable. Statement of the theorem. The precise statement of the most basic version of Taylor's theorem is as follows. Taylor's theorem. Let k1 be an integer and let the function f r be k times differentiable at the pointer r. Then there exists a function hk r such that this is called the Peano form of the remainder. The polynomial appearing in Taylor's theorem is the kth-order Taylor polynomial of the function f at the point A. The Taylor polynomial is the unique asymptotic best fit polynomial in the sense that if there exists a function hk r and a kth-order polynomial p such that then p equals pk. Taylor's theorem describes the asymptotic behavior of the remainder term, which is the approximation error when approximating f with its Taylor polynomial. Using the little o notation, the statement in Taylor's theorem reads as explicit formulae for the remainder under stronger regularity assumptions on f. There are several precise formulae for the remainder term rk of the Taylor polynomial, the most common ones being the following. Mean value forms of the remainder. Let f r be k plus 1 times differentiable on the open interval with f continuous on the closed interval between r and x. Then for some real number L between r and x. This is the Lagrange form of the remainder. Similarly, for some real number C between r and x. This is the Cauchy form of the remainder. These refinements of Taylor's theorem are usually proved using the mean value theorem, whence the name. Also other similar expressions can be found. For example, if g is continuous on the closed interval and differentiable with a non-vanishing derivative on the open interval between r and x, then for some number xi between r and x. This version covers the Lagrange and Cauchy forms of the remainder as special cases, and is proved below using Cauchy's mean value theorem. The statement for the integral form of the remainder is more advanced than the previous ones, and requires understanding of Lebesgue integration theory for the full generality. However, it holds also in the sense of Riemann integral provided the th derivative of f is continuous on the closed interval a, x. Integral form of the remainder. Let f be absolutely continuous on the closed interval between r and x. Then due to absolute continuity of f on the closed interval between r and x, its derivative f exists as an L1 function, and the result can be proven by a formal calculation using fundamental theorem of calculus and integration by parts. Estimates for the remainder. It is often useful in practice to be able to estimate the remainder term appearing in the Taylor approximation, rather than having an exact formula for it. Suppose that f is times continuously differentiable in an interval I containing a. Suppose that there are real constants q and q such that throughout I, then the remainder term satisfies the inequality if x greater than a, and a similar estimate if x less than a. This is a simple consequence of the Lagrange form of the remainder. In particular, if on an interval I equals with some r greater than 0, then for all x. The second inequality is called a uniform estimate, because it holds uniformly for all x on the interval. Example: suppose that we wish to approximate the function f equals x on the interval -1, 1, while ensuring that the error in the approximation is no more than 10⁻⁵. In this example we pretend that we only know the following properties of the exponential function. From these properties it follows that f equals x for all k, and in particular, f equals 1. Hence the kth-order Taylor polynomial of f at 0 and its remainder term in the Lagrange form are given by where xi is some number between 0 and x. Since x is increasing by, we can simply use x1 for x minus 1, 0 to estimate the remainder on the subinterval minus 1, 0. To obtain an upper bound for the remainder on 0, 1, we use the property e she less than x for 0 less than she less than x to estimate using the second-order Taylor expansion. Then we solve for ex to deduce that simply by maximizing the numerator and minimizing the denominator. Combining these estimates for x, we see that so the required precision is certainly reached when, as a conclusion, Taylor's theorem leads to the approximation. For instance, this approximation provides a decimal expression E2.71828, correct up to 5 decimal places. Relationship to analyticity. Taylor expansions of real analytic functions let IR be an open interval. By definition, a function f(IR) is real analytic if it is locally defined by a convergent power series. This means that for every AI there exists some r greater than 0 and a sequence of coefficients ckr such that I and in general, the radius of convergence of a power series can be computed from the Cauchy-Hadamard formula. This result is based on comparison with a geometric series. And the same method shows that if the power series based on a converges for some BR, it must converge uniformly on the closed interval, a minus RB, a plus RB, where RB equals B minus A. Here only the convergence of the power series is considered, and it might well be that extends beyond the domain I of F. The Taylor polynomials of the real analytic function f are simply the finite truncations of its locally defining power series, and the corresponding remainder terms are locally given by the analytic functions. Here the functions are also analytic, since their defining power series have the same radius of convergence as the original series. Assuming that a minus r, a plus r, I and r less than r, all these series converge uniformly on. Naturally, in the case of analytic functions, one can estimate the remainder term rk by the tail of the sequence of the derivatives f at the center of the expansion. But using complex analysis, also another possibility arises, which is described below. Taylor's theorem and convergence of Taylor series. There is a source of confusion on the relationship between Taylor polynomials of smooth functions and the Taylor series of analytic functions. One can see the Taylor series of an infinitely many times differentiable function f(RR) as its infinite-order Taylor polynomial at A. Now the estimates for the remainder of a Taylor polynomial imply that for any order k and for any r greater than 0 there exists a constant mk, r greater than 0, such that, for every x, sometimes these constants can be chosen in such way that mk, r0 when k infinity and r stays fixed. Then the Taylor series of f converges uniformly to some analytic function. Here comes the subtle point. It may well be that an infinitely many times differentiable function f has a Taylor series which converges on some open neighborhood of A, but the limit function tf is different from f. An important example of this phenomenon is provided by using the chain rule. One can show inductively that for any order k, for some polynomial pk of degree 2, the function tends to 0 faster than any polynomial as x0, so f is infinitely many times differentiable and f equals 0 for every positive integer k. Now the estimates for the remainder for the Taylor polynomials show that the Taylor series of f converges uniformly to the 0 function on the whole real axis. Nothing is wrong in here. The Taylor series of f converges uniformly to the 0 function tf equals 0. The 0 function is analytic and every coefficient in its Taylor series is 0. The function f is infinitely many times differentiable, but not analytic. For any k and an r greater than 0 there exists mk, r greater than 0 such that the remainder term for the kth-order Taylor polynomial of f satisfies Taylor's theorem. In complex analysis, Taylor's theorem generalizes to functions which are complex differentiable in an open subset UC of the complex plane. However, its usefulness is dwarfed by other general theorems in complex analysis. Namely, stronger versions of related results can be deduced for complex differentiable functions f, u, c using Cauchy's integral formula as follows. Let r greater than 0 such that the closed disk Bs is contained in U. Then Cauchy's integral formula with a positive parametrization gamma equals z plus right of the circle S with t, 0, 2 pi, gives here all the integrands are continuous on the circle S, which justifies differentiation under the integral sign. In particular, if f is once complex differentiable on the open set U, then it is actually infinitely many times complex differentiable on U. One also obtains the Cauchy's estimates for any z u in r greater than 0 such that BSU. These estimates imply that the complex Taylor series of f converges uniformly on any open disk BU with SU into some function Tf. Furthermore, using the contour integral formulae for the derivatives f, so any complex differentiable function f in an open set UC is in fact complex analytic. All that is said for real analytic functions here holds also for complex analytic functions with the open interval I replaced by an open subset UC, and decentered intervals replaced by C-centered disks B. In particular, the Taylor expansion holds in the form where the remainder term Rk is complex analytic. Methods of complex analysis provide some powerful results regarding Taylor expansions. For example, using Cauchy's integral formula for any positively oriented Jordan curve gamma which parametrizes the boundary WU of a region WU, one obtains expressions for the derivatives f is above, and modifying slightly the computation for Tf equals f. One arrives at the exact formula. The important feature here is that the quality of the approximation by a Taylor polynomial on the region WU is dominated by the values of the function f itself on the boundary WU. Similarly, applying Cauchy's estimates to the series expression for the remainder, one obtains the uniform estimates. Example: the function f r are defined by its real analytic, that is, locally determined by its Taylor series. This function was plotted above to illustrate the fact that some elementary functions cannot be approximated by Taylor polynomials in neighborhoods of the center of expansion which are too large. This kind of behavior is easily understood in the framework of complex analysis. Namely, the function f extends into a meromorphic function on the compactified complex plane. It has simple poles at z equals I and z equals minus I, and it is analytic elsewhere. Now its Taylor series centered at z0 converges on any disk B with r less than z minus z0, where the same Taylor series converges at zc. Therefore, Taylor series of f centered at 0 converges on B and it does not converge for any zc with z greater than 1 due to the poles at I and minus I. For the same reason, the Taylor series of f centered at 1 converges on B and does not converge for any zc with z-1 greater than square root 2. Generalizations of Taylor's theorem. Higher order differentiability. A function f Rn is differentiable at Rn if and only if there exists a linear functional L Rn and a function h Rn such that if this is the case, then L equals df is the differential of f at the point A. Furthermore, then the partial derivatives of f exist at A and the differential of f at A is given by introduce the multi-index notation for alpha nn and xrn. If all the kth order partial derivatives of f Rn are continuous at Rn, then by Clairaut's theorem, one can change the order of mixed derivatives at A. So the notation for the higher order partial derivatives is justified in this situation. The same is true if all the th-order partial derivatives of f exist in some neighborhood of A and are differentiable at A. Then we say that f is k times differentiable at the point A. Taylor's theorem for multivariate functions. Multivariate version of Taylor's theorem. Let f Rn be a k times differentiable function at the point Rn. then there exists H alpha Rn such that if the function f Rn is k plus 1 times continuously differentiable in the closed ball B, then one can derive an exact formula for the remainder in terms of th-order partial derivatives of f in this neighborhood. Namely, in this case, due to the continuity of th-order partial derivatives in the compact set B, one immediately obtains the uniform estimates example in 2 dimensions, for example, the third-order Taylor polynomial of a smooth function f.